This talk covers some of the interesting aspects of LayerCake's architecture. First, I'll provide an architecture overview. I'll talk about the parsing and code generation framework and the implementation of dynamic mode and the component types, followed by a description of the template language and how it works. So first, the architecture. LayerCake's architecture is composed of two main sections. The green boxes are the dynamic runtime, and the blue boxes are the compiled runtime. So the dynamic runtime is used for parsing LayerCake code, doing the code generation, and the implementation of the dynamic mode. But when you only have compiled layers, the dynamic mode code goes away. In general, the dynamic runtime is 70,000 lines of Java code, which is fairly small given all that's going on. And the compiled runtime is less than 10,000 lines of code, and it runs on JavaScript and Android. There are two types of generated code in LayerCake. The generated code that comes from compiled types just depends on the blue LayerCake runtime. And the code for interfacing a dynamic type with compiled code is in a dynamic stub, and that depends on the dynamic runtime as well as the compiled runtime. Let's talk about the parselet's parsing and code formatting framework, because this is one of the most innovative aspects of LayerCake's architecture. It's a single declarative grammar that both parses code into a language model, also known as the abstract syntax tree, and it watches for changes made to that language model and goes back in the reverse direction and updates the code in an incremental fashion. And the grammar that's used is actually compositional, so the LayerCake grammar extends Java, and the template language grammar extends the LayerCake grammar. So let's look at some examples. The first example here is the line terminator, and it's a choice of three symbols, \r, \r, \n, and the first one that matches wins and produces a line terminator. And then kind of skipping down to a more interesting construct, here is the grammar definition for the while statement in Java. And there are three components to the while statement: the keyword, the paren expression, and then the statement. And when each of those matches, an instance of the class while statement is created, and its operator property is set to the keyword, the expression property is set to the value of the paren expression that matched, and the statement property is set to the value of the statement that's matched. And this, is fairly similar to some other parsing frameworks, but what's unique is that when you change the expression or change the statement, it will regenerate the code representation by updating just the piece that changed. And then another grammar definition is the type identifier, and this is an ordered choice, and it can either be a primitive type or a qualified identifier. So the primitive type would be an int, float, etc., and the qualified identifier is like the Java lang string. Given the power of LayerCake's grammar definition, the code for grammars is actually still pretty small. There's a base language that has about 200 lines of grammar definition, and Java extends the base language and adds 600 lines of grammar definition for the complete Java language. And then LayerCake extends the Java grammar and adds only 75 lines of code, and the template language extends LayerCake and adds only 50 lines of grammar definition. Now let's skip to the processing phase. So when LayerCake code changes, it gets converted to Java, and this leverages the code formatting or code generation aspects of the parselet's framework to incrementally transform a LayerCake language model into a Java language model. And there are two ways that it can be done. One is that you can just modify the model from code. So take a statement, add it to another class definition, add it to the body of a method, etc., and the code will just get updated automatically. And the other way is when you have a big block of code that needs to get processed, you can apply a code template. So this would be a parameterized chunk of text that turns into code once we evaluate the template. Then we reparse that code and take the definitions that get produced and add them to the model at the right spot. So this is how the object operator is processed, or a field is converted into getSet methods. And the way this works is all incremental. So if you have a pure Java file that you put in a LayerCake extension, none of the model needs to get converted, and that code just passes through unchanged. And in general, LayerCake's parselets framework will preserve comments and the code structure, etc. And I believe that makes the system's generated code more debuggable and maintainable. Let's look at the implementation for dynamic layers. Dynamic layers implement a complete LayerCake code simulator optimized for run once code. They provide full Java compatibility even when interfacing with compiled code. If necessary, a stub class is generated to map the compiled class's runtime contracts into the dynamic contract. This requires a system restart whenever a stub class which has been loaded already needs to change. For example, the first time you override a compiled method or change the compiled class you extend. LayerCake warns you when a restart is required to apply a given code change. Dynamic layers are always stacked on top of compiled layers. In this picture, dots represent classes, objects, and properties. Solid lines represent compile time relationships, and dashed lines represent dynamic relationships. When a dynamic layer modifies a compiled type, it makes that a dynamic type even if the type is defined in a compiled layer. This system gives you a flexible and robust way to partition your code into dynamic and compiled layers. As your system evolves, you compile more layers in your application and more types become statically defined. Even when your system has millions of lines of code, since you are compiling the code which is not changing and interpreting the code which is, you retain rapid development even for large systems. Now let's look at the implementation for component types. They're implemented by applying a code template with high-level parameters. When you're generating an object, a getX method is implemented, which creates that component. And when it's a class, a new X method is generated. And if you're in an inner class, those methods are part of the enclosing class. If you're at a top-level class, there's a static method. So this lets you use components and objects even from non-LayerCake code, as long as you know the naming convention for how those methods are defined. The goal of the component implementation is to support multi-phase initialization and arbitrary graphs of objects. So this involves moving the constructor code out of the Java constructor and into a method so that we can construct all the objects, we can wire up all the graphs so that all the reference graphs are assigned, then we can run the constructor code. And then there's a pre-init method that's run after assigning the references. And when one component is created, it initializes and starts all of its reference components in order. So it gives you an efficient, fast way to kind of create and define a whole object graph. Let's look a little bit more deeply into the template language. It's a nested code and text, a lot like JSP, and uses some of the same conventions. So the document starts out as text, and you can use less than % to break into code, and % greater to break back into text. There are also two other operators. You have less than % exclamation mark for declarations, and the first of those, if a declaration is the first code in the file, then that becomes the type declaration. So a template can be any arbitrary LayerCake class just using a declaration. When you use less than % followed by statements, you can put any arbitrary Java or LayerCake statements inside the template, and those can output content to the document just like in JSP. or you can use less than % equals with a LayerCake expression, and that expression is evaluated and placed into that location in the document. Unlike JSP, when you're in a code section, you can break back into a template section wherever you have a string. So you can take any string and you can replace it with %, followed by an arbitrary text section, then less than % to come back into code. So this is kind of like turning JSP inside out. And of course, those text sections can also embed further expressions themselves. That same pattern also works so that you can replace statements with a body of text, and that text will turn into something like an out.append call, depending upon the context of where those statements occur. The template language is very flexible. It can be either interpreted or compiled like other LayerCake types, and it's highly configurable and used to implement code templates that we've seen. There's a servlet with an LCSP suffix that's implemented in just a few lines of code, or you can generate XML with an LCXML file, and a layer can define a new template format and customize the names of the methods, the base class, etc., so that you don't have to write a lot of code to get a very flexible system, and you can generate whatever you want from a template. Okay, in summary, LayerCake's architecture gives you a lot of power from a very small, well-designed code base. I believe it offers a no-compromises solution, which is a low footprint, low overhead for compiled types, and a very quick round-trip time for dynamic types. In general, it's an efficient platform for future language and framework development. Thanks for watching.